All right, welcome to ECE 164, Lecture 12 on the GM over ID design methodology. So if you recall back in homework 1, we attempted to extract Kn prime, where Kn prime can be written as 2ID divided by W over L, VOV squared, for a square law model. And what I went ahead and did is I extracted this as a function of VOV and also looked at different channel lengths. And what you can see is that this extracted value for Kn prime, it depends heavily on the channel length as well as the overdrive voltage. And so even for our relatively old technology in this class, this value cannot be viewed as a constant parameter. And so you could be finding yourself asking, well, why is this deviating from the square law model? What effects are causing this? And then more importantly, that's fine, but how would I design with a device like this when I can't even know a fundamental parameter like Kn prime? Is there a simple way to describe this behavior? We're going to deal with this in the following way. We are going to learn a systematic simulation-based device characterization, and we'll talk about some of the physical phenomena that underlie this behavior as we go through. So the basis of this characterization looks at fundamental figures of merit that relate directly to circuit design. And so in particular, the one that's probably the most common is what's called the transconductance efficiency. So in analog circuit design, we often want large transconductance, large GM. And the price that we have to pay to get this transconductance, or the currency, is current. And so it makes sense to look at the transconductance efficiency as the ratio of GM divided by ID. That is what I want and what I have to pay to get it. For a square law model device, this is equal to 2 divided by VOV. We talked already about the transit frequency. This is a metric of how fast the transistor is. Oftentimes we want large transconductance, and we don't want to have large capacitance. And so the transit frequency is the ratio of these two quantities, that is GM over CGG, or the total gate capacitance, which in the square law model is roughly equal to 3/2 mu times VOV divided by L squared. Okay. And then lastly is the intrinsic gain of the transistor. Again, we want large GM, but we don't want any slope to the ID curve as a function of VDS. That is to say that we want infinite output impedance. Okay, and so G naught is 1 over R naught, the conductance of it, and so the intrinsic gain is GM R naught, or GM divided by G naught. And this is equal to roughly 2 over lambda times VOV. Okay. Importantly, you'll notice that these quantities all in some sense make sense. In particular, if I want high transconductance efficiency, that really means that I want very low overdrive voltage. Okay, so I want to minimize the overdrive voltage, put the device either in sub-threshold or right at the edge of moderate inversion. If I want a transistor to be very fast, that means lots of overdrive voltage, high mobility, but more importantly, short channel length devices. And this is where newer technologies really benefit, is they have intrinsically shorter channel length. And then lastly, this lamp for the intrinsic gain. This means increasing lambda, which we know is a strong function of L. So increasing the channel length as well as decreasing the overdrive voltage again. Okay, so how do we do this device characterization? We would set up a netlist that essentially sweeps the input voltage, VGS, while biasing the transistor at VDD over 2 and setting W over L. In this case, we want to set W to a nominal width that's certainly above the minimum width, usually 20 to 30 times the minimum channel length. And then what we're going to do now is we're going to sweep this. We're going to sweep VGS, and then we're going to probe or measure several quantities. We're going to measure the overdrive voltage. We're going to measure GM over ID. We're going to measure FT, and we're going to measure GM R0. All right, so then we can put this together into this plot. Okay, and so this plot I'm showing GM over ID, or the transconductance efficiency, on the y-axis. This has units of Siemens per amp. On the x-axis, I'm showing the overdrive voltage, or VOV. Starting off with an NMOS, this is actually what we simulated. And so, again, low overdrive voltage, we have the highest transconductor efficiency, where we're biasing the device literally in subthreshold, because right at VOV is 0, anything to the left of this is subthreshold. What you'll notice, though, is this deviates quite a bit from our ideal MOSFET. So I also, to this plot, added 2 divided by VOV for anything below moderate inversion. So moderate inversion, recall, is about 150 millivolts overdrive voltage. These two curves look nothing alike, okay? And so that's why in 164, we have been using biasing VOV greater than 150 millivolts to get us out of this subthreshold or near 0 VT behavior, okay? 0 VOV. You will notice that this has a pretty good relationship out here, and that's how we've been able to design a lot of our circuits and have the hand calculations match the simulations fairly closely. And then lastly, for reference, I'm adding a BJT. And so if we're to calculate the GM over ID, or the transconductor efficiency of a BJT, it's simply KT on Q, or excuse me, 1 over KT on Q, or 1 over the thermal voltage, which is right here at about 40 millisiemens, or excuse me, 40 Siemens per amp. And it's a constant. It doesn't depend on the overdrive voltage, as a BJT doesn't really have an overdrive voltage in the same way that a MOSFET does. Okay, so some quick observations. Again, the square law is fairly close for overdrive voltage greater than 150 millivolts. It does a terrible job when VOV is less than that, matching the square law. It deviates significantly. GM over ID, or the transconductor efficiency, does not approach infinity for VOV is equal to 0. And I think the takeaway from the previous slide should be that we can never do better than a BJT. So a BJT, regardless of where we bias the MOSFET, will always have better transconductor efficiency. Okay. And so now, in order to kind of continue on this, I want to show you where the regions of operation are on this particular curve. So for subthreshold, we're going to have VOVs less than 0. The behavior here is like a BJT. It was very flat on the previous slide, and GM over ID is nearly constant. This will all make sense in just a second when we kind of go through the rationale why. In moderate inversion, when we have VOV less than 150 millivolts, this is the transition from different carrier mechanisms, and so we get this interesting mix of true MOS-like behavior and BJT-like behavior, and that's why we try to avoid this region of operation. And then strong inversion, the deviations here are primarily due to any kind of short channel effects that we're going to see from the MOSFETs. Okay, so looking a little bit more closely at the subthreshold current, for a BJT, we can write that the collector current is equal to the saturation current times the exponential of VBE divided by VT, where VT is defined as KT on Q, or 25 to 26 millivolts at room temperature. For a MOSFET that's in subthreshold, we have a very similar equation where ID is equal to I0 times the exponential of VGS minus VT, the threshold voltage, divided by N times the thermal voltage. Okay? Here in this case, this N is really just a capacitive divider. It's a divider between the junction or the gate capacitance as well as the oxide capacitance. And in our technology, it's roughly about 1.5. Okay, and so recall that if we have a transistor, That's our oxide. We get one capacitor that's formed here, okay? And then we also get a depletion capacitor that's formed down here that on this side we're calling CJS. And so this is COX, this is CJS, this is the gate, and this is the substrate. And so this is where we're getting this capacitance division that's making this device act like a BJT, but attenuating the actual current that we're going to get. So that's why this is about 1.5 times lower. All right, so again, if we look at an NMOS and compare it to a NPN, on the y-axis here, we're showing the current in log. On the x-axis, I'm showing VBE or VGS, the controlling voltage for these different transistors. And what you can see is that the BJT has a linear on a log relationship here, whereas the MOSFET, we don't start to pick up and flatten out until after VT. So before VT, it's very similar to the bipolar device. After VT, it flattens out quite a bit. The BJT, this is what's called low-level injection, and this is high-level injection for the different device. And so that's why it tapers off at the ends as well. All right, so if we look back at the GM of this device, if I was to take the partial derivative of the drain current with respect to VDS, I would get that it's 1 over N times ID over VT for a MOSFET in subthreshold. And GM over ID is then 1 over NVT. And so if you look at this plot, this was our BJT. And if we go down roughly 1.5x from, just rounded up, call it 40, we end up at 25. So this is actually relatively good behavior, and it matches what we would expect from theory here. Now, once we move to moderate inversion, this is where things are interesting. And they're interesting because there's two different carrier current mechanisms or current carrying mechanisms that are happening. A MOSFET is primarily a drift-based device. That is that the carrier velocity is proportional to the mobility and the electric field, whereas a BJT is primarily a diffusion-based device, and so it's proportional to the concentration gradient of these carriers. It turns out that these two are always present in all modes of operation. It's just that in moderate inversion, neither of them really dominates the carrier action, and so it's this weird mix between the two of them. And so you can actually show that the ratio of the drift to diffusion current relates to the overdrive voltage, VOV, divided by the thermal voltage. And once we get above a few kT on Q or a few thermal voltage, this drift mechanism quickly starts to dominate the behavior. And so that's why we get good matching with our square law model in that case. Okay, so to recap our GM over ID plot, in this region here, below VOV is equal to 0, this is what we would call subthreshold. And subthreshold is very similar in behavior to a BJT, albeit attenuated by that capacitive divider ratio. Then we start to transition into moderate inversion here. Okay, and then once we get out of moderate inversion, then we move to strong inversion. Okay, and so the question is kind of what's going on up here in the strong inversion case? Why is this green curve slightly above this blue curve? Can we explain this type of behavior? This is really due to all of the short channel effects that we talked about back in the device lecture. So we have things like velocity saturation. This is due to that very large lateral electric field. We have mobility degradation due to the vertical electric field. Essentially, we're pulling all of the carriers up to near the surface where it's very rough and we have a lot of defects in the lattice. And so the mobility of the silicon goes down. The VT dependence on the channel length and the channel width. This is effects like DIBBLE, like drain-induced barrier lowering, coming into play here. We also know that VT is a function of VDS, R naught is a function of VDS, and on and on. So there's many short channel effects that are causing all of this. We're going to focus mainly on these two up here. So we're going to talk about the velocity saturation and the mobility degradation in order to establish a qualitative understanding of what's going on in these plots. So velocity saturation, again, recall back from lecture 1 or 2, where we derived for a square law model that the carrier velocity was proportional to the lateral electric field. Okay, so that is that when we have a device and I have carriers in the channel, their velocity, V, is proportional to their mobility, as well as the electric field that is propelling them along this horizontal axis. Okay? However, we talked about that at very short channel lengths, we can have a large voltage drop across a very short distance. And so what this means is that we can have very, very large electric fields. Okay? And at a certain point, the carriers just start bumping into the lattice and they can't go any faster. Okay? So this is a lot like driving down the freeway, or I should say pre-COVID, was like driving down the freeway at 5 o'clock. You just kept bumping into a lot of cars, and even if you had a Ferrari, you couldn't get it up to 100 miles an hour. Okay? Same thing here. The carriers want to go faster, however, they're limited by all of the other stuff around them at the time. And so if we look at the velocity as a function of the electric field, what we see is that for low electric fields, we have a relatively linear proportionality like we'd expect, and then we start to fold over, okay? And when it's folding over, this is really the short channel effect, that we're getting limited by the velocity of the carriers, or we have what's called velocity saturation. Okay? And so the way to model this is that we can write the velocity as a function of the electric field, which is mu E divided by 1 plus E divided by EC, where EC is the critical electric field that we can't go past. And so when we get to the velocity saturation, it's this critical electric field that will limit how fast we can go, which eventually saturates and plateaus at the short channel length velocity saturation equation when we have E is greater than the critical field. Okay, so in the plot, there's a couple of different regions that are kind of important. One, in the low field region, all of the long channel equations that we've used are still valid because we don't ever reach this critical electric field. In moderate field, the long channel equations or the square law model, they start to become somewhat inaccurate. And once we get to very high electric fields, the velocity saturates completely and is essentially constant regardless of the voltage that we apply across it to get that horizontal electric field. So to get a kind of a better handle of this, I want to show you what the electric field is using some very simple calculations, and then we'll look at the critical field and the voltages required in order to get these critical electric fields. So in saturation, the lateral field across the channel is going to be equal to the overdrive voltage. That's the voltage that we have to drop across VDS, divided by the channel length. And so let's take very simple numbers, 200 millivolts overdrive voltage, 0.18 minimum channel length device. This gives us about a 1 megavolt per meter electric field. So in our device for a NMOS, the critical electric field is about 6.7 megavolts per meter. Okay, and so what we see is that even applying 200 millivolts, which is a nominal overdrive voltage, we're only at about 15% of the critical field. So we need to apply much more than 200 millivolts in order to get truly to that critical field. Okay? So at 200 millivolts, we are going to see some impairments, but they're relatively minor. Okay? If we apply a larger VOV, however, as you do in digital circuits where VGS or VSG are equal to the supply voltage, I mean, if you take a simple example like an inverter, in this inverter, I apply a VDD or a ground to the input, and I get the same swing on the output. Okay? What that means, though, is that the overdrive voltage across this NMOS or this PMOS is very, very large. Okay? I mean, close to VDD minus the threshold voltage in both cases. All right, so what does this look like if we wanted to actually patch up our ID equation in order to calculate this? We talked about this back in lecture 2 as well, but essentially what we do is we add this band-aid onto our expressions, our ID expression that includes the critical electric field and the channel length in order to limit it. And if you want, you can kind of think of this as a parallel combination where the critical field times the channel length and the overdrive voltage are essentially in parallel, which takes this from a quadratic VOV relationship to just a linear VOV relationship. Okay? And to get a better feel for this, let's just look at some numbers again for 0.18. If I had the critical electric field times L, 6.7 megavolts per meter times 0.18 micron, that gives me an overdrive voltage of 1.2 volts. Okay? For a PMOS device, the critical electric field is a little bit higher. It's about 16 megavolts per meter, and that gives me an overdrive voltage of 3 volts. Okay? And so what this says is that even in our 0.18 technology, you could hit the critical electric field, especially in digital circuits, you definitely do, with a 1.2 volt overdrive voltage applied to the transistor. If we have VOV is much less than the critical field times the length, we can show that GM over ID is 2 divided by VOV times this band-aid that we added onto the previous slide. And so if we look at an NMOS device, again, with 200 millivolts of overdrive voltage, we would get a transconductor efficiency of 2 divided by VOV times 0.86. Okay? And it's this 0.86 that's causing that reduction. So if you recall back to those GM over ID curves, the square law model was just slightly above the simulated model by about this 15%. Okay? And so this is in very good agreement with the simulation data that we have from this technology. All right, so moving on to the mobility degradation, recall back that if we think about a transistor, and we have carriers in the channel, it's not just the horizontal electric field that's acting on these carriers. So the horizontal electric field is moving the carriers from the source to the drain. However, we've inverted this channel, and in doing so, we're trying to pull these carriers up. And so there's a vector that's acting on these particles, partially in the horizontal plane as well as the vertical plane. Okay? And this has been getting worse. It's been getting worse in part because we've been making this oxide thinner. Okay? We've been making this oxide thinner with various technology nodes in order to have better control over the charge that's in this channel. Okay? And to give you numbers of how this has changed, in 0.35 micron, the oxide was about 6.5 nanometer thickness. In 0.18, it decreased to 4 nanometers, and then it went to 1.8 nanometers in 90 nanometer CMOS. Okay. Unfortunately, once you start to get this oxide to be too thin, you also get current that can tunnel. And so what that means is that there's a gate current now. So all of this time, we love MOSFETs because they don't have gate current like BJTs, and we always thought gate current was difficult to deal with. And it turns out that in highly scaled CMOS process nodes, we have to deal with that there as well. I should note that after a while, they stopped decreasing the gate oxide thickness because it became too difficult to deal with the current. And they also started to change the gate oxide to be what's called high K dielectric, where high K dielectric let them increase the gate oxide thickness to recover the gate current leakage, but also still have good control over the charge that was in the channel. So as a result of this, the electric field in the device has been increasing, and it's trying to pull the carriers closer and closer to this, what I'll call dirty silicon surface. Why is this dirty? Recall that the channel itself in here, this is crystalline silicon. I mean, this is perfect lattice. That's why it gets very, very high mobility for the carriers here. At the surface, there's a lot of defects. I mean, you can imagine that this is broken bonds, kind of unstructured lattices and defects, and all of that is right near a transition from a silicon to a silicon dioxide. Okay, and so this rough surface is what gives rise to this dirtier silicon, and these imperfections slow down the carriers as they move through this, and they also give rise to this effect of what's called 1/f noise, which you'll learn about much more in 264A. So how do we deal with this in our equations? We can replace the mobility term with an effective mobility. Okay, and so we'll have this effective mobility replace mu and be a function of the voltages that we're applying to the device. So this mu f, or mu effective, is going to be approximately equal to mu divided by 1 plus theta times the overdrive voltage. Okay, and this theta term is going to have 1/volts, and it will range typically from 0.1 to 0.4. Okay, and so what you see here is that as we increase the overdrive voltage, we degrade the mobility further and further, which should make sense. We're increasing this force vector, pulling the carriers closer and closer to the surface. I do want to point out that all of these things that we're adding on to our ID expression are really band-aids. They're fudge factors meant to try to patch up this this long channel square law model and make it somewhat match these short channel devices. At a certain point, it just becomes cumbersome to try to deal with all of these, and you realize that a better methodology is needed in order to even capture any of this behavior. Okay, and so that's where, the square law model is good for understanding fundamental device behavior, but when we actually get to designing circuits, especially in deep sub-micron technologies, we need a different methodology that's a little bit more encompassing of what the device actually does. Okay, so now moving on to look at the transit frequency. Again, this is all from that same simulation that I showed you back on like slide 5. Here we're looking at the transit frequency ft on the y-axis in gigahertz as a function of the overdrive voltage. Okay, and so what you see is that for this particular technology, the square law model would predict that we just keep going up and up and up and up as we increase the overdrive voltage. Turns out that that's not the case, that the device has a very shallow tail down here when we're in sub-threshold, increases linearly with this curve for a little bit, and then it starts to plateau off. And so we start to see significant deviation here. The other interesting thing worth pointing out right now is that you can see essentially what this technology is capable of. And so if we go back here for a 0.18 minimum channel length device, this technology is roughly capable of about 35 gigahertz of FT. So some observations from this plot. Again, the square law model did not do a very good job, especially in subthreshold and in strong inversion. We saw very large discrepancies. The reasons for these are exactly the same ones that we've already discussed when we were looking at GM over ID. It's really the bipolar action in subthreshold and the short channel effects when we have large overdrive voltage. We get lower GM, and hence GM divided by CGG goes down. So the same conclusion, we won't be able to make good predictions with simple square law relationship. We really need a better methodology in order to move forward. So to quickly look back at GM over ID and GM over CGS, we see an interesting relationship, right? So here, GM over ID is equal to 2 divided by VOV, and GM divided by CGS, or FT, is equal to 3/2 mu VOV divided by L squared. So the interesting thing about this is that the FT improves as we increase VOV, and the transconductor efficiency decreases as we increase VOV. And so this kind of leads to this contradiction that I'm summarizing in the table down here. With small VOV, I get large GM over ID, but small FT. For large VOV, I get small GM over ID, but large FT. And so the question is, is there a sweet spot? Is there somewhere where I can bias the technology that I'm going to get kind of the best of transconductor efficiency for FT? And so what you can do is you can look at the product of these. You can look at GM over ID times GM divided by CGS. This is the transconductor efficiency times the FT. And we'll get that if you use the square law model, this is equal to 3 mu divided by L squared. Okay? And so again, this L squared term shows you that we should benefit in terms of performance by going to newer and newer technology nodes. And that's really what's driven Moore's law continually, is to decrease the channel length so that we can squeeze better performance out of the transistors while simultaneously cramming more transistors within a given area. So if we do plot this, it looks a little bit boring. It's a constant, right? So this constant says that we should be able to bias this anywhere, and we get a constant product. Smaller channel lengths improve circuit performance, and we can use that smaller channel length to get better speed or better current efficiency. However, if you actually do the plot for the real technology, taking into account all of the non-idealities, we see a much more interesting plot. And so here, what we're showing is GM over ID times FT, that same quantity that we calculated previously. But rather than getting a flat line, we get this interesting curve that shows that there really is an optimum place to bias the transistor. At the lower end down here, the square law is predicting too much transconductor efficiency. And so that's where we deviate from kind of this flat line that we normally had. At high overdrive voltage, we start to kick in a lot of channel length modulation effects, short channel effects. So we decrease the transconductance, and that leads to kind of this sweet spot. And the sweet spot, it moves around for different technology nodes, but it's usually right about 150 to 200 millivolts. And here we have the maximum product of GM over ID, transconductor efficiency, times FT. Okay, so last, let's talk about the intrinsic gain of the device. So the intrinsic gain I'm showing here as GM divided by GDS. This is the same as GM R naught. again, versus the overdrive voltage. Our long channel model predicts a 1 over lambda ID expression, and so that would be shown here for lambda is equal to 0.3. And in actuality, the simulated curve is a lot flatter, okay? And it actually starts to decrease, interestingly, when we have higher overdrive voltage. And so I would say that there's no Band-Aid that's going to fix this curve. We really cannot get close to this anywhere with our lambda model equation. Okay? These two curves are just fundamentally very different. And this is why channel length modulation or the output impedance of circuits is always something that we should be very skeptical that the models are accurate for as well. We never want to design circuits that rely heavily on RO or RDS. Okay, so if we look back at our curves, there's another thing that's kind of interesting. Here we're plotting VDS as a function of ID. And what we see is that, looking at the slope of this for that same transistor biased with 100 millivolts, now if we look at GDS, so 1 over GDS, this is the output impedance R0, again, as a function of VDS, it's relatively flat. And we do see that at VDS is equal to VOV, we're significantly below the maximum value. And so what this shows you is that if you bias the transistor right on the edge of saturation, right at this point where VDS is equal to the minimum, we don't have very good output impedance. Okay? And so this is why, for example, in current mirrors, when we use the magic battery, we typically don't use it exactly at VOV, but we'll bias it at 1.5 or maybe even 2 VOV in order to shift the output impedance up so that our current mirrors have good output impedance without having to bias them a full VT above. If we zoom in a little bit further onto these curves, again, here's VOV that's annotated, and what we can see is that when we have VDS is equal to 2 divided by GM over ID, we're roughly at about half of the final value of this, okay? And it turns out that this is actually how the simulator defines this quantity that's known as VDS sat. So VDS sat is defined arbitrarily as the VDS at which 1 over GDS is equal to 1/2 of the value at VDS, which in our case is equal to VDD divided by 2, or 0.9 volts. Okay. And so again, we're showing overdrive voltage down here, and what we see is that for the VOV as a function here, this is a linear function, VD sat, and then I'm also showing 2 divided by GM over ID. And again, this is where we come up with this definition of VD sat, where once we get about 4 kT on Q above this minimum voltage, we have a reasonable estimate of what VD sat is. Okay. If you're familiar with the terminology of V star, this is another quantity that is a reasonable estimate of VD sat. So that's V star is typically 2 divided by GM over ID. So a couple of observations that we can take away from this intrinsic gain plot. One, the device shows a rather gradual transition from triode to saturation. The square law predicts a very abrupt change when we go to saturation, and so we get this very large intrinsic gain change. And the V star is a reasonable way to estimate the minimum VDS that we actually need to extract gain from this device. And so rather than just use VOV, 2 divided by GM over ID is a better bias point for that. As I mentioned earlier, you'll typically want to bias it a little bit above this just for safety so that you don't crash down and start to reduce the output impedance dramatically, especially in current mirrors where you're very sensitive to the output impedance and trying to design for very high R out. I don't want to get too deeply into the physics that govern the output impedance. They're very complicated, and due to many different effects, such as channel length modulation, which we talked about and gave a good first order treatment to, but also things like drain-induced barrier loading, substrate current-induced body effect. And some of these, I should mention, are not in all technology and even all devices within a technology. Sometimes PMOS devices don't have SCBE, depending on how they're manufactured. If you really want more details about this, I'd refer you to a device physics textbook or a class where you will spend the better part of the quarter talking about some of these advanced topics. Okay, so we're back to kind of this question. We've now realized that the square law model is not adequate for deep submicron CMOS, but also we can't use the simulation models. So the models can have 400 or 500 different parameters, and so we can't do hand calculations with that. And so there's this weird problem where we can't use square law model because they're not accurate enough, yet we have too complicated equations to do hand calculations. So how do we make this tractable? This is where a lot of designers tend to fall into this trap of just doing what's called spice monkeying. Okay? Spice monkeying is where you have no hand calculations and you just keep messing around in spice until the circuit somehow works. This typically results in a couple of things. One, the design is usually not very robust, given that the designer himself or herself doesn't really know fundamentally what is influencing these parameters. They're just sweeping parameters around, trying to find parameters that work or a design space. And two, anytime they have to redesign the circuit for new specs, they essentially have to resort to the same spice monkeying behavior. And so in general, this is something that we absolutely want to avoid. We want hand calculations in order to drive our design decisions. And then we need a method now in order to make these models tractable for hand calculations. And that's where we get into this, what's called GM over ID design methodology. We want a systematic design methodology that doesn't need or require these entire MOSFET equations. And so the strategy here is to revert back to lookup tables. And so we can make tables that characterize the technology and use these tables in order to do hand calculations and even size the devices. And so the tables that we'll work on are FT versus GM over ID, ID over W versus GM over ID. ID over W, this is what's called the current density. This tells us how large we need to make a device in order to carry the current. And then GMR naught as a function of GDS. Okay. And so essentially what we're going to do is we're going to get specifications for the circuit that we want. We may do some square law hand calculations to get us relatively close. Okay. We'll pick an architecture, we'll do some spice simulation, and then we'll calculate the results. Okay. What we are trying to do here is find a way to incorporate these BSIN models back up into our hand calculations. Okay. And that's where making these tables takes the actual device parameters that the simulator is going to use, and we incorporate them back into our hand calculations such that now when we simulate, these two are going to match. And they're going to match very well because we are using the exact same BSIN models or PSP models that the simulator is using as it's going in. So we no longer have a disconnect between our model and the model that the simulator is using, which means that our specifications and our results are also going to match much better. Okay, so how do we actually do this in practice? we're going to plot the parameters for a reasonable range of GM over ID and L, and we're going to generate these three plots that I talked about before: transit frequency, intrinsic gain, and current density, all of these versus GM over ID. Okay. If you want to get a little bit more advanced, you can also calculate estimates of extrinsic capacitances. So recall that FT is the intrinsic capacitance, or CGS. At times, we've also wanted to know how CGD and CDD were relative to CGG. And so we can calculate or tabulate these as well. And the neat thing about this is that all of these parameters that we're going to talk about are to the first order independent of the device width. Okay? And so that means that I don't have to set up this massive database of values. I can literally make these charts once, print them out, or even incorporate them into my optimization loop, things like MATLAB or Excel, in order to read these charts and size the devices as I see fit. Okay. So if you've ever done filter design, this is actually quite similar to when you use coefficient tables in calculating all of the different components of the filters. Okay, and so now what we're going to do is we're going to simulate for our technology channel lengths from 0.18 micron to 0.5 micron in steps of 20 nanometers. And so on the x-axis down here, this is VOV. On the y-axis, I'm showing two curves. One is GM over ID, the other is FT. So these are GM over ID, and these are our FT curves. If we repeat the same thing for PMOS curves, we sweep the device with exactly the same length steps. Again, GM over ID here, FT here. We now can take these and we can start to put them into the tables that we want to compute. And so here, this is the transit frequency chart. And so all that I'm doing is taking the data on the previous slide and manipulating the axes such that I have GM over ID on the x-axis, FT on the y-axis. And you can see that as I increase the channel length from 0.18 micron all the way up to 0.5 micron, the maximum FT is going down. Okay, and so this intuitively should make a lot of sense. Lower channel length is going to mean higher overdrive voltage. Biasing this transistor with a lower GM over ID means higher overdrive voltage. That's also going to result in a higher FT. This is the intrinsic gain. And so again, GM over ID on the x-axis, GM R naught on this y-axis. And what we see is that for our minimum channel length device, biasing this at roughly GM over ID of 15 or 20, even up here, this is in sub-threshold. We have an intrinsic gain of about 40. As we start to increase the channel length, we can increase the GM R naught up to about 100 for an NMOS device in this technology. This current density plot showing ID over W versus GM over ID. Again, minimum channel length device up here and increasing down to half micron device at this size. Okay, and so the way that we'll use this plot is that if I want to bias a transistor, for example, at GM over ID of 10, okay, and I take this point for a 0.18 micron channel, and that means that I'm going to set the current equal to 30 amps per meter. Okay, so the current density. And so once I know the current through this device, this allows me to size the width of the device. Now I have W, now I have L, and I've biased this transistor at the GM over ID that I want. And so the other thing that you can see is that for sub-threshold, when we start to get up kind of GM over ID of 15 to 20 and even a little bit beyond, I have to make the devices very large in order to to have the same amount of current passed through the devices. And so the width and the length of the devices for sub-threshold grow quite dramatically. All right, so what we can do in 164, I've actually characterized the GF technology, and I've made MATLAB scripts that have all of this. And so I will post this on Canvas. The use of this is pretty straightforward. First, we're going to load up this quote unquote database, and then we're going to use lookup functions to look up the device. And so the first function is the technology. If there's multiple technologies, I parameterize this such that you can replace this with whatever technology you're using. The second parameter is the device. So if there happen to be multiple devices in the technology, as you'll find very, very commonly in newer technology nodes, you can choose the device here, the channel length, and the gmId. And so what this gives us back is this is the FT, the transit frequency for this particular device. And so we get 36 gigahertz for FT. Similarly, if I wanted to look up the gmId, I have the technology, the type of device, the length, and I can give it an FT value, and it will tell me what gmId to bias it at. Same thing for ID over W. In this case, I'm looking up a PFET device. There's also a few other lookup functions. Feel free to look in the folder at these various different functions. So we should ask ourselves a couple of things, and that's all of these plots I generated way back kind of at the beginning with a VDD over 2. Okay, and so what I'm showing you here is I'm sweeping VDS for a couple of different voltages from 0.9, 0.4, and 1.4, and we're looking at ID over W. Okay, and it turns out that it just doesn't change much. There's a relatively weak relationship between the current density and this VDS. And so what this means is that we don't need to make very complicated charts in order to do this. We can work with nominal VDD over 2, and so that's where we'll characterize the technology. Here I'm showing the capacitances in the device. Again, channel length of 0.18 micron, and I'm sweeping VDS for this device, and I'm plotting the ratio of either CDD divided by CGG or CGD divided by CGG. Okay, and so what we see is that the drain current is roughly 60%, and CGD is roughly 24%. Again, very similar before about the voltage that we're looking at. These curves, there is some dependence here, but they're relatively flat. And in particular, the CGD one is extremely flat as a function of VDS. And so typically people will just work with VDD over 2 numbers. This is again looking at the extrinsic capacitances, but now we're looking as a function of channel length. And as you might expect, they do change as a function of channel length as we increase the length of the device, in particular for CGD. The CGD capacitance is fixed. It's the overlap capacitance, but CGG, the gate capacitance, is going down as we increase the length, and so this ratio also decreases. CDD, for similar reasons, as a function of the gate capacitance, decreases. Okay. Again, both of these are because these two quantities are not really a function of the channel length. CGG is a function of the channel length. And here's the same simulation, but now for a PMOS device. We see very similar numbers across the board. Okay, so how would I actually use this in the design of a circuit? I'm going to walk through an example where we will use this methodology as well as the lookup charts. So first thing we're going to do is we're going to determine the transconductance that we want. Okay, and this is typically going to be driven by one of the design objectives, maybe the open loop gain, for example. Then we're going to pick a channel length This is a little bit of up to the designer to explore, in the sense that you have to use your intuition and your previous experience to rely on roughly how to choose the channel lengths. You can be guided by the following, that if you want a very short channel, you would typically do that if you need a lot of FT, if you want a high-speed circuit, for example. On the other hand, if we're trying to make a lot of gain, you would typically use a longer channel length device. And so in analog circuit design, as a rough rule of thumb, you'll typically design transistors with 2 to 3x the minimum channel length. Almost always you'll avoid using the absolute minimum channel length unless you're pushing very hard on high-speed circuits. All right, then we're going to go through and we're going to pick either GM over ID or FT. It really depends on our design and what's more important, in the sense if we're trying to design for high speed, FT is more important. If we're trying to design for higher gain, then maybe GM over ID makes a little bit more important. Keep in mind that GM over ID is the efficiency of the circuit. Okay, and so if we have large GM over ID, that typically means that we're operating in sub-threshold. It's going to be a lower powered circuit, and we may have larger voltage swing due to our low VDS sets. On the other hand, small GM over ID, this is good for high-speed circuits where we're going to get a lot of FT, but we also have to spend a lot of overdrive voltage and current in order to make that happen. Once we have GM over ID or FT, we can determine the ID. Again, this is directly from knowing GM up here and then using GM over ID. We multiply these together and we can get the current out. Once we have the current, we can determine the width from the normalized current density plots. And I should point out that there are a lot of different ways of doing this, but in general, this is more or less how the design is going to flow. One of the last things that we're going to do is look up the width of the device. Some of these can move around in terms of their order. It very much depends on the particular circuit that you're trying to design. Okay, so let's do an example. We've designed this circuit many times in this course. We've seen it several times. It's a common source amplifier. We have a model of a transducer where we have a DC bias at the input, small signal voltage. Ri is the output impedance of this transducer or previous amplifier stage. We have a load capacitance and a load resistance that are being biased by a bias voltage VB, such that none of our bias current flows through this RL. Okay. So we're going to set up a couple of specifications. One, that we're going to design this in our 0.18 micron technology. We're trying to get a DC gain of -4. This load resistance is 1 kilo ohm. The capacitance is 50 femtofarad. The input resistance is 10 kilo ohms. Okay. And our objective is not to minimize the power in this case, but to maximize the bandwidth while given a fixed current of, or a current less than 300 microamps. Okay. And so again, thinking through kind of our design choices here, this maximizing the bandwidth with this relatively low gain. I mean, we're not trying to make a ton of gain here, just -4. This would really drive us towards choosing a minimum channel length in this particular technology. Once we did that, we would go through and calculate out GM from the gain and this load resistance. Then we can determine the device width, and then we can estimate parameters like the poles and the non-dominant pole in order to understand the bandwidth. All right, so here's the small signal model of the circuit. You'll notice that I've combined a couple of capacitors together in order to simplify our calculations. And the first thing that we're going to do is calculate the necessary GM and GM over ID. So we know that we're trying to get a a magnitude of our gain to be 4, which is equal to gm times R naught parallel RL. RL is only 1 kilo ohm, and so we're going to safely neglect R naught in this case. That gives us a transconductance of 4 millisiemens. If we use all of our bias current and be very greedy, that gives us a transconductance efficiency of 13.3 Siemens per amp. A fair question is, why can we neglect R naught? We can justify this by calculating the intrinsic gain of the device. And so if we look at the real gain expression, it's equal to gm times RL parallel RO. I can simplify this or rearrange the equation by writing 1 over RL plus 1 over R naught, multiplying through by the gm term here. 1 over the gain is equal to 1 over GMRL plus 1 over GMR naught. Okay. This GMRL term, we know what this is. This is going to be equal to 1 over 4. GMR naught in our technology is, for a minimum channel length device, it's greater than 30. It was closer to 40. It's very safe to neglect this 1 over 40 term relative to this 1 over 4 term. Okay, and so R naught is not going to affect our gain in this problem. Okay, so what about the frequency response of this? We know that there's going to be a 0 from CGD. That 0 is at GM over CGD, which is going to be much, much greater than the transit frequency FT of this device. So the 0 is never going to come into play in this picture. The dominant pole, we can calculate this. It's likely going to be at the input, given our source impedance was being fairly large. And so if we go back to lecture 6 on the common source amplifiers, we can calculate out what the dominant pole as well as the non-dominant poles are for this. Okay, so this is just doing KCL, KVL, analyzing the circuit in order to come up with these design expressions. We can then calculate the capacitances from our parameters. So we know that CGS plus CGB is equal to CGG minus CGD. Again, CGG is all of the gate capacitance, so anything that touches this gate. So CGG itself is defined as CGS plus CGB plus CGD, as well as CDD is everything that touches the drain node, which is CDB plus CGD. All right, so now we can calculate CGG from FT. And so in our particular example, we're at 13.3 Siemens per amp at a 0.18 micron channel length. And so that gives us an FT of roughly 16.9 gigahertz. From this, we can now find the capacitances CGG, CGD, and CDD, where they're all shown here. So CGG is going to be roughly 40 femtofarad, CGD is 9 femtofarad, and CDD is 20 femtofarad, which places our poles at 197 megahertz and roughly 5 gigahertz. All right, so now how do we size this device? We use our current density plot, again coming back to GM over AD of 13.3, 0.18 micron channel length, and this gives us a current density of 16.2 amps per meter. And so now when I want to calculate the width is going to be equal to ID divided by this current density, ID over W. And so for 300 microamps of current, this is going to give me an 18.5 micron device. Okay. All right, so now when I'm setting up my simulation circuit, I'm going to use replica biasing in order to bias up the DC voltage of this. And so what that means is that I'm going to take a replica of this node here, putting 300 microamps, diode connecting this transistor with the same W, the same L, and then using this to bias up the actual amplifier. I'm adding a very large, extremely large capacitance here of 1 farad in order to decouple this and not contribute any poles or any frequency response from the bias circuit itself. Over here, I've replaced this with 0.9 volts, and everything else is exactly from the specs that we got driving a 1 kilo ohm and a 50 femtofarad load. Okay? So let's simulate this. So looking at the operating point first, ID, the simulation has 326 microamps. Our calculation was 300 microamps, so we're within 10%. GM was 4.16 millisiemens. We were aiming for 4 millisiemens. Again, we're within 10%. CD, CGG, CGD, all of these were extremely close. Okay, GM over ID, the calculated GM over ID, we're within 10% on all of these, and we didn't try to influence anywhere we were on the design, and we also used a minimum channel length, which is, to be honest with you, the worst case for a lot of these parameters. And so the reason that we're so close is because we use this normalized design space. We use these tables that were generated from the transistors, and all of the equations that govern their behavior in the simulator, we use those for our hand calculation via these tables. Okay? And so that's why we get such good agreement with this relatively straightforward procedure. In terms of the capacitances, looking a little deeper at some of these capacitances, these all were very close to our hand calculations, and I'm just showing you the definition for a lot of these capacitances here. They vary based on the technology. Some technologies call these slightly different things. In our case, this is how the capacitances are defined. Okay, so how does this actually simulate out? Running an AC simulation on this circuit, we ended up with 11.5 dB of gain, which is approximately 3.8. Our first pole was at 213 megahertz, and our second pole was at 5 gigahertz. Again, hand calculation, we were aiming for a gain of 4, so we're within 10%. Our pole is actually very close, well within 10%. For both of our dominant and our non-dominant poles. Okay, so what can we take away from this? One, I would say that our pole, our frequency response were spot on. And they were spot on because we really took into account all of the capacitances. The other discrepancies that we saw in terms of the DC biasing and the gain, these are typically on the order of about 10%. And almost always they're due to VDS dependence and finite output resistance that we don't really want to go into the trouble to deal with. The reason that we got such good agreement was, again, using pre-computed tables that SPICE itself generated. And so that's why it's very useful to do this technology characterization. And then as you go through the design, we already have this, we've done it once, and we can use this for many different designs. I will say that if there are discrepancies, it's usually pretty easy to track them down because we have all of the canned calculations that we can literally directly compare against things that matter. So rather than ending up with fictitious values, we, in our design calculations, use things like GM, ID, FT. These are directly measurable and observable from the transistor itself, rather than things like mu, which we couldn't even get good parameters for anyway when we were trying to simulate it. So I would consider these to be artificial parameters that really don't have significance on the SPICE model. So coming back to our circuit, what if we wanted to maximize the bandwidth, but also keep the current consumption as low as possible? We took a greedy approach in the sense that you said we could use 300 microamps from our specifications, and that's exactly what we biased it at. If we keep the assumption that that the input impedance and the load and the gain are fixed, these are specs that are probably driven by a larger system level analysis. Okay? And so what we can show is that we can write the bandwidth as 1 over Ri times CGS. This is the pole at the input. And I'm going to start to rearrange these parameters based on things that we can control. So CGS we know is 2/3 WL Cox. GM is equal to mu n Cox W over L times VOV. And the gain is equal to GM times R. And so plugging all of these back into this omega 3dB equation, we see an interesting relationship. Okay, this is equal to 3/2 mu divided by L squared. These are all technology parameters. So nothing that I can do as a designer changes mu, other than I can play around with kind of keeping it out of short channel effects such that I don't end up with degradation. The channel length, I can pick the minimum, but after that, there's nothing that I can do. It's set by the technology. And then we see the second set of parameters here, where the resistance divided by the, this is the load resistance divided by the gain times the input resistance. These are really the specifications. And so again, me as a designer, I can't do anything about these specifications. They're fixed. Lastly, we see that this depends on VOV. This is my one in this particular circuit design knob. This is my design variable where I can play with VOV, and that's how I trade off bandwidth for power consumption. And so if we look at this kind of from a GM over ID methodology, we can write that GM is equal to 2ID over VOV. Again, the gain of the circuit is equal to GM times R. And so the current is equal to 1/2 times the gain divided by R. This is to get GM times VOV. Okay, again, specs, design knob. Okay. And so what can we see from this? One, we should be increasing VOV in order to get larger bandwidth, but the current is directly proportional to this VOV. And so your job as the analog circuit designer is to choose VOV such that you get enough bandwidth while we're using as little current as possible. So this is where you as the designer are optimizing the circuit for performance in order to minimize the power consumption. And so even though we've done this for a really simple circuit, in general, this trade-off holds for a lot of circuits. There will always be some second order dependencies that we'll learn about later on as you continue your journey in analog circuit design. But the general trend here is very simple to see, and we've proved it multiple different ways. There's going to be a trade-off in terms of bandwidth and power. And ultimately, these rely on fundamental trade-offs within the transistor itself. If you want to think about this in terms of what you want to get out of the MOSFET, if you want a large GM without investing much current, you want a large GM over ID. That's large transconductor efficiency. We want a large transconductance, but we don't want any capacitance. That is, we want a large FT, right? And so these two drive the decisions, and these are also the things that we are using in our normalized calculations of GM over ID methodology. And so I want to briefly, before we end, talk a little bit about scaling and what scaling is doing to the technology. So Moore's law, as I mentioned earlier, continues to shrink the minimum channel length over time. And there's really nothing fundamental about Moore's law. It's really that the billion-dollar semiconductor industry strives to maintain this scaling. And so what we've seen over the past 40 plus, 50 plus years now is that the channel length has decreased roughly 2x every 5 years. And so to put up some data points for you, back in 1970, the minimum channel length was roughly 10 micron. Fast forward 37 years, and this was decreased to 45 nanometers. In 2020, right now, we're currently designing and fabricating circuits in 5 nanometers. And so we've continued to decrease the channel length very strongly as a function of time. And what we see is that we can exploit the technology in various different ways. If I want to build faster circuits, I can keep the power efficiency constant. This lets me get to higher performance. Things like spinning disk drives, where we want to spin the disk drive faster and faster. We want to maximize the bandwidth or the throughput, but we want to keep the power efficiency constant. It also means that we can build more efficient circuits that have higher GM over ID. And so the way to think about this is that for a fixed amount of bandwidth, I need less and less of that bandwidth. And so that allows, when I go to a newer technology node, as a fraction of FT, and so that allows me to bias the transistor in deeper and deeper subthresholds. Okay, and so a good example here is when an A to D converter is fixed by a standard. For example, for video transcoding, there are specs on the transmission frequency, so I don't need to run the A to D converter any faster, but I would like to reduce the power consumption. Okay, so to summarize this lecture, the GM over ID design methodology, it's a very powerful technique. It allows us to harness a lot of the short channel effects and incorporate them into our design, even when they become very dominant. And this is most pronounced not in this 0.18 technology, but as you move farther and farther into deep submicron technologies, a la 32 nanometer was probably one of the worst technologies because it was the last planar technology, and then they started to go to 3D transistors like FinFET. This is a very powerful technique to abstract away things like what region of operation, what overdrive voltage, and instead we shift the performance to normalized metrics, things like the transconductor efficiency, the transit frequency, and the intrinsic gain of the device. And then lastly, one of the most powerful things about this is that we can automate the lookup tables and incorporate them into design flows. And so oftentimes what I've done in the past is I will have a script that designs, for example, a folded cascode amplifier given a technology file, as well as a handful of different specs. And so this is literally just me running MATLAB that pops out all of the W's and all of the L's for various different, for all of the different transistors in the circuit. And then when I go simulate it, it's almost always spot on because I've used the technology that's been characterized with these lookup tables. Thank you.